is goal of this lecture? Today I will see reducible test and irreducible test of a polynomial. Actually, this topic, reducible test and irreducible test of a polynomial, this topic is very important for any competitive exam. Not only CSIR NET, GATE, ISI, for all competitive exam, this topic is very important. We all of us know what is the irreducible polynomial. Let R be integral domain. And a non-zero non-unit polynomial fx is called irreducible polynomial over R if there exists gx and hx in Rx such that fx can be written as gx times hx. Then either gx is a unit or hx is a unit. If we can write two product of polynomial, if fx can be write to product of polynomial, then either the one polynomial is unit or other polynomial is unit, then we can tell fx is irreducible polynomial. And reducible polynomial means if fx equal to gx times hx such that gx hx belongs to Rx, both are non-unit. If both polynomial are non-unit, then fx is called reducible polynomial. Fx equal to x square minus 2 over q. Over q, we can tell fx is not reducible. That means fx is irreducible polynomial. Because over q, we can write this as 1 times x square minus 2. Here 1 is the unit element over q. So over q, this is the irreducible polynomial over q. But over R, we can write this polynomial, this fx, we can write this as x minus square root of 2 times x plus square root of 2. Over R, we can reduce fx such type. Here, not this polynomial or this polynomial be unit. Both polynomial are belongs to Rx, but they are not unit. Because unit in Rx look like constant polynomial. So, this is reducible over R. Similarly, fx equal to 2x square plus 4. This is irreducible over q, but reducible over z. Because fx equal to, we can write 2 times x square plus 2. This is irreducible over R because 1 over 2 is the unit element in Q. 2 is unit in Q because multiplicative inverse of 2 is 1 over 2. But 2 is not unit in Z. So, fx equal to 2x square plus 4 is irreducible over q but reducible over z. Have you understood? Okay. Fx equal to x cube plus 1. We can factor this polynomial as x plus 1 times x square minus x plus 1. This is not unit element in these two polynomial is not unit element in R, Q or C. Similarly, these two polynomial not unit in Z also, because in Z only unit element are plus 1 and minus 1. So this polynomial is reducible over R, Q, C and integer both. One irreducibility test is root test. A polynomial fx belongs to fx which is degree 2 or degree 3 polynomial is irreducible if there exists a belongs to the field f such that f of a not equal to 0. If f of a not equal to 0, then we can tell the polynomial is irreducible. Obviously, this polynomial must be degree 2 or 3. For degree 2 and 3, this condition is if and only if condition. But when the degree greater than 2 or greater than 3, then this condition is not necessary condition but sufficient condition. If f of a equal to 0, if there exists a root, then we can tell about reducible, but we cannot tell about irreducibility. If f is a field and degree of fx is 1, if degree of fx 1, then fx is irreducible over the field f. As for example, fx equal to 2x plus 6 and x minus 6. Here degree of the polynomial is 1. So since R or C are field, so fx are irreducible over R or C. But if f is not field, then the above result need not be true. Fx equal to 2x plus 6 is reducible over z. Also, if fx belongs to zx and degree of fx greater than 1, then fx always be reducible over c. As for example, x square minus 3, fx equal to x square minus 3. This is reducible over the c. Similarly, if fx belongs to zx and degree of fx greater than 2, then fx always reducible over r. As for example, if fx equal to x to the power 4 plus 1, then fx is reducible over r. If fx in zx and fx is reducible over q, if fx is reducible over q, then we can tell always fx is reducible over z. Also, second result, if fx belongs to zx and fx is irreducible over z, then fx always irreducible over z. But if fx is irreducible over q, then fx is irreducible over z when fx which belongs to zx is primitive. Then we can tell fx is irreducible over q, imply fx is irreducible over z. Primitive means if fx equal to a0 plus a1x up to an x to the power n, then primitive means GCD of a0, a1 up to an always would be equal to 1. Okay? When GCD of a0, a1 up to an would be equal to 1, then we can tell the fx is primitive. That means when fx is irreducible over q, then that imply fx is irreducible over z when the function is primitive. Otherwise this is not possible. But when fx is reducible over q, then that imply always fx is reducible over z. Example, fx equal to x cube plus x square plus 1 over z2. Notice f0 equal to 1 and f of 1 equal to 3, and mod with mod 2 this value would be 1. Since degree of polynomial is 3, degree of fx is 3, so by root test we can tell fx is irreducible over z2. There exists a nice result if fx is irreducible over zp for some prime p, and degree of fx over q same as degree of fx over zp, then we can tell fx is irreducible over q also. That means if fx is irreducible over zp where p is a prime number, then we can tell fx is also irreducible over q. That means here by this result we can tell fx is irreducible over q. And since the polynomial is primitive polynomial, GCD of 1, 1, 1 equal to 1, so we can tell fx is also irreducible over z also. That means fx is irreducible over z2, z over z and over q. Next example, fx equal to x to the power 4 plus x cube plus x square plus x plus 1 reducible over z5. Since here the question about reducible, so here we can use root test. Root test only applicable degree 2 and degree 3, but sufficient condition of root test is always true if degree greater than 3 and if there exists a root, if f of a equal to 0, then we can tell obviously the function the fx is irreducible over this field, but we cannot say irreducibility over the field. Fx may or may not be irreducible over the field when degree greater than equal to 3. Here notice f of 0 equal to 1 and f of 1 would be 1 plus 1 plus 1 plus 1 plus 1, and in mod z5 this value would be 0. So we can tell this polynomial is reducible over z5. Also we can tell this polynomial is reducible over z. Let's see Einstein's irreducibility test. Let fx equal to a0 plus a1x plus a2x square up to an x to the power n belongs to zx. Suppose that for some prime p, if p divide a0, p divide a1, p divide a2 up to p, if p does not divide an, also p square does not divide a0, then we can tell fx is irreducible over the polynomial over q. Let R be integral domain and fx equal to a0 plus a1x up to an x to the power n x, then if fx is reducible if and only if its reciprocal polynomial and its reciprocal polynomial let's denote as gx, and its reciprocal of fx would be an plus 1x up to a naught x to the power n. If fx is reducible, we can tell its reciprocal polynomial also reducible, and this is the if and only if condition. So, if by Einstein criteria, Einstein irreducibility test, we can tell there exists some polynomial for this fx is irreducible, then their reciprocal of this function also irreducible by this polynomial, because this is the if and only if condition. So, suppose fx equal to a naught plus a1x up to an x to the power n. Suppose there exists a polynomial prime, there exists a prime p such that p satisfy the reciprocal of this polynomial. That means at first p satisfy here p divide a1 up to p divide an, but p does not divide a naught and p square does not divide an. This is this p. For this p also by Einstein criteria, because this p is satisfied for the reciprocal of this polynomial, because if we apply the mod p test in the reciprocal of this polynomial, then this would be satisfied. For such case also by Einstein criteria, we can tell fx is irreducible over q. Okay. Now as for example, if fx equal to x to the power 5 plus 6x plus 12, notice if we consider p equal to 2, here an is x to the power 5 order, this is coefficient 1, and a naught is 12. Notice 2 does not divide an means 1, but here 2 divide a1 6, 2 divide 12, but 2 square means 4 divide also, this is the a naught term, 4 divide also 12. So, we cannot choose p equal to 2. Next, we can choose p equal to 3. For this, 3 does not divide 1 means an, 3 divide 6, 3 divide 12, but 3 square means 9 does not divide 12. For p equal to 3, Einstein's irreducibility test has satisfied. So, by this prime, we can tell fx is irreducible over q. Notice here this is very important things. For some prime, if we can choose those type of prime for this Einstein irreducibility test would be applicable, then we can tell fx is irreducible over q. I hope my all viewers have understood clearly this test. Okay? Well. Now I will see one example which had come CSIR NET December 2019 exam. The question is, let fx belongs to zx be a monic polynomial of degree n. That means GCD of coefficient is 1. Option A, if fx is irreducible in zx, then it is irreducible in qx. Few minutes ago I have got one result. When fx is irreducible in zx, it is imply irreducible in qx. Option B, fx is irreducible in qx, then it is irreducible in zx. There exists a lemma, Gauss's lemma, about irreducible. A non-constant polynomial in zx is irreducible in zx if and only if it is both irreducible in qx and primitive in zx. When primitive, the polynomial is primitive, that means GCD of coefficient is 1, then irreducible in qx imply irreducible in zx. But irreducible in zx always imply irreducible in qx. I have got this result. This is the if and only if condition. When the polynomial is primitive. That means option A and option B is the right option. I hope my all viewers have understood clearly how the result is very important, how the result has applicable here. Okay. Next, if fx is reducible in zx, then it has a root. It has real root. Notice, consider fx equal to x square plus 1, x square plus 2. This is reducible in zx because here the coefficient belongs to z. Also, this fx can be reduced to polynomial where none of them are unit. So, fx is reducible since the coefficient of this polynomial belongs to zx. So, fx is reducible in zx. But notice here the root are plus minus I and x square plus 2. These are root plus minus square root of 2i. That means this has complex root. So, fx is reducible in zx means this does not imply this is always be real root. So, option C also wrong option. For this, if fx has real root, then it is reducible in zx. For this, consider one polynomial. Consider x has a root plus minus square root of 5. Then that imply fx equal to x square minus 5. That means we can write this polynomial as such type: x plus square root of 5, x minus square root of 5. Here notice the coefficient are plus 1 square root of 5 plus 1 minus square root of 5, which does not belongs to integer. So, this polynomial has a real root, but it is not reducible in zx because the coefficient are not belongs to in z. So, option D also wrong option. I hope my all viewers have understood clearly how we have to solve any polynomial be reducible or irreducible. This test actually very important for any competitive exam. Okay. In my next video, I will discuss some more tests to find reducible or irreducible polynomial. Okay. See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.